We've seen by now how first-order differential equations can occur in various simple physical circumstances, and we've been able to solve some of them quite easily, but we haven't learned enough techniques to solve all kinds of first-order differential equations that are actually important. And this is what we're going to do in this lecture. I'm going to talk about first-order linear differential equations in this lecture. Now, earlier we'd seen that any differential equation of first order could be written in the form dy by dx is some given function of x and y. And this function of x and y could have been anything. It could have 0 powers of y, 1 power of y, 2, 3, etc. But if it had 2 or more powers of y, it would then not be a linear differential equation. So let's see what a differential equation could be. So over here now I'm going to take f of xy simply equal to x cubed sine of x. This is a linear differential equation. If I add to this, let's say x squared y, that too is a linear differential equation because it's got only 1 power of y over here and only one derivative of y here. On the other hand, if I had this, dy by dx is x cubed sine x plus, let's say, x squared y squared, that would not be a linear differential equation. Now, in calculus books, you'll see the standard form of a linear differential equation written down in this way. So dy by dx plus some function of x times y is some other function of x. And both p and q are given. This equation would have to be solved for y. Now, you'll also see this written as y prime plus p of x y equals q of x. But that's exactly the same thing. Dy by dx is y prime. So an example would be, let's say, y prime equals 3y plus, let's say, tan x. And that, of course, is a linear differential equation. On the other hand, sometimes you'll find equations written down in this way, and then you must then convert it into the standard form. And in this case, you'll do this by dividing both sides by x squared tan x. So you get y prime plus, then I'm dividing over here log of x squared by x squared tan x. And this side also 3 over x squared tan x times y plus 7 over x squared tan x. And so let's put this into standard form. Y prime plus minus 3 over x squared tan x times y equals 7 minus log of x squared divided by x squared tan x. So now it's very clear that this over here is q of x. So this is q of x. And this over here is p of x. So this equation has been converted into this standard form. And now we learn how to solve equations that are put into standard form. First order differential equations, the standard form for which is given over here, can always be solved. And there's a systematic way of doing that. And that systematic way requires us to calculate what is called an integrating factor. That integrating factor is a function v of x. It's commonly called v, you could call it anything else. And this will be determined by a requirement that we'll come to shortly. So let me write the equation up above exactly the way it is. dy by dx plus py is equal to q. And now let me multiply both sides of this equation with v. So this is v times dy by dx plus v times py equals vq. Now I'm going to require that this be equal to d by dx of v times y. So this is the requirement that will determine v ultimately. We'll come to that shortly, finding v. But suppose that there is such a way of writing what's up above in this manner. Well, then we've gone a long way towards the solution, because then you have d by dx of v times y equals v times q. And so let me take dx on that side. This becomes v times y, rather d of v times y equals vq dx. V is a function of x, q is a function of x. Let's integrate both sides. So we get v times y equals integral dx v times q. And so from here we get the solution. Y of x is then 1 over v of x integral of v of x q of x. And that is the result that we want, because it's telling us that if this integrating factor v of x is known, then all we need to do is calculate this integral. So the next task is find v of x. Okay, we will do that from the following requirement. That's up above over here. V dy by dx plus v p of y must be equal to d by dx of v times y. Let's see what that gives us. So v dy by dx plus v times py. This must be equal to d by dx of this, but d by dx of this is dv by dx into y plus v times dy by dx. We have the same thing here and here, so that cancels, and y can also be divided out. So then we are left with v times p equals dv by dx. This is an equation that we know how to solve, because from here we have dv by v equals p dx. And so this then tells us that if we integrate both sides, so we can just integrate both sides over here, this tells us that log of v is equal to integral p dx. And so we have our result for v of x. This is the integral, or rather the exponential of the integral of p of x dx. So e to the power integral p of x dx. Let me write this. So v equals e to the integral p dx is the answer that we were looking for. Calculate v from here first, put it in here, and you get the answer for y of x. We'll now solve a number of examples using the formula that we derive for the integrating factor. First, consider this linear differential equation. It's linear because the maximum power of y is 1, and we've been given an initial condition as well. Let's first divide by minus 2x to put this into the standard form that we have over here. And so that makes it dy by dx minus 2 over x y equals half x. And so that immediately tells us that p of x is minus 2 over x and q of x is half x. So let's first calculate the integrating factor. That v of x is then e to the integral dx, and p of x is from here minus 2 over x, so dx over x, which integrates to log of x. So this is e to the minus 2 log x, and if you like, you can write this as e to the minus log of x squared. Now, this is 1 over e to the log of x squared, and e to the log of something is that something, so this is equal to 1 over x squared. So we have the integrating factor. Now, let's find y of x, and this is 1 over v of x, so that's x squared. And then we need to do this integral, so 1 over x squared, and q of x is half x, so that's half x here, and that makes it half x squared integral dx over x, and that makes it half x squared into log of x plus a constant. Now this here is called the general solution of this differential equation, which means that the constant c is not determined. It could be anything, positive, negative, or whatever. And now let's use this specific condition that y of 1 is equal to 2. So when x is 1, y is 2, and that means that 2 is equal to half, x is 1, log of 1 is 0, and there's just c over there. And so that says that c is equal to 4. So the particular solution, this is as opposed to the general solution, which is what we want with this specific condition, is that y of x is half x squared log of x plus 4. This is the solution to this linear differential equation. Let's get some more practice. Here's another linear first order differential equation. It's already in the standard form up above over here. So clearly p of x is tan of x and q of x is then just half cosine squared x. There is no initial condition that has been provided, and so we'll be able to get the general solution only. First, let's calculate v of x, and that is e to the power integral of p of x, so that's the integral of tan of x. Now the integral of tan of x you can immediately get because this is minus log of cosine of x. Why is that so? Because if you differentiate log of cosine of x, you get 1 over cosine of x, and then when you differentiate cosine of x, you get minus sine of x, so the minuses cancel. And so log of cosine of x is the antiderivative of tan of x, minus tan of x. So we now have over here e to the minus log of cos of x, and this then is 1 over log of cos of x, and that's 1 over cosine of x. So v of x is now 1 over cosine of x. The only thing now is to integrate this over here. So 1 over v of x is then cosine of x, and here we have to integrate v of x, which is this, times q of x, which is half cosine squared x. So this thing is cosine of x into half integral of cosine of x. And of course, everyone knows how to do that. This is half cosine of x, and inside we will have sine of x plus a constant. So since cosine of x, sine of x is half of sine 2x, you could write this a little better by writing this as 1/4 sine 2x plus half, or just write c times cosine of x. It doesn't matter whether you call this half c or c, because as it is, c is undetermined unless one gets some initial conditions. So this is the general solution to this equation. So far we've dealt only with linear first order differential equations, but this over here is definitely not a linear equation, because q of x over here is multiplied by y to the power n, and n can be anything. But the famous mathematician Bernoulli showed that by changing variables, he could convert this into a linear equation. So define a new function, call it h of x, that's to be written in terms of y in this manner. So h is y to the power 1 minus n, in which case, if we want an equation for dh by dx, we'll have to differentiate this. So write this as dh by dx. We differentiate first with respect to y, get 1 minus n into y to the minus n, and then we have to differentiate y with respect to x. So that gives us, obviously, dy by dx is 1 over 1 minus n y to the power n dh by dx. And now let's put this in here. So we get 1 over 1 minus n y to the n dh by dx, and then here p of x times y, and this is q of x y to the n. Now divide both sides, so take this over here and divide both sides by y to the n, in which case what we get is 1 over 1 minus n dh by dx plus p of x, and when we divide y by y to the n, we get y to the 1 minus n, but that's just equal to h, so that becomes h here, and this is q of x. That's all. And so if we put this into standard form, this is dh by dx plus 1 minus n into p of x, h equals 1 minus n q of x. So essentially we've got the same type of equation that we had previously, except that this over here is multiplied by 1 minus n, so call this a new function p prime of x, and this over here is almost the same as before except for this factor of 1 minus n, and that's q prime of x. So now we have exactly the same situation, and now we can use the integrating factor and solve this equation for h. Once we know h, well then we can get y from here. So from here, y will be h to the power 1 over 1 minus n. In this way, we are able to solve this equation. But now let's work out an example. Let's solve this nonlinear differential equation using the trick suggested by Bernoulli. First, put this into the standard form. So it's dy by dx plus y over x equals 1 over xy squared. Now we'll use the Bernoulli trick, define h is y cubed, and this is the essential part. The new function h is defined in terms of the old function y, and what we need is a differential equation in terms of h. So dh by dx is 3y squared dy by dx. And instead of using dy by dx and dh by dx, let me save some space by writing this as h prime is equal to 3y squared y prime. And now y prime is h prime over 3y squared. Let me put that in over here. So h prime over 3y squared plus y over x is 1 over x y squared. Now what I'm going to do is multiply both sides of this by 3y squared. And so this then gives me h prime plus 3y cubed over x equals 1 over x times 3. But y cubed is just h. And so what we've got now is h prime plus 3 over x h equals 3 over x. And now this is an equation that we know how to solve because this is exactly of the standard form that we're used to. So let's find the integrating factor v of x, which is e to the integral p dx, and this is our p. So this is p, and this is, when we refer to the standard form, q. And now this then integrates to e to the 3 integral dx over x, which is e to the 3 log of x, which is the same as e to the log of x cubed, which is the same as x cubed. So we have the integrating factor now. All we need to do now is find h of x. So h of x is 1 over the integrating factor cubed. You must have remembered the formula by now. There's the integral over x of x cubed. The integrating factor comes again over here, and then we have to multiply by q of x, so that's 3 over x. That then is 1 over x cubed, and when we integrate 3x squared, we get x cubed plus a constant. And so this becomes 1 plus that constant divided by x cubed. We're not going to be able to find the constant because we've not been given any kind of initial value, but this is now h of x. And so we have found the solution to this equation. We just take from here y is h to the power 1/3. And so y of x then is 1 plus c over x cubed to the power 1/3. And that is the solution to this nonlinear first order differential equation. Just one comment. Suppose I take c equal to 0. In that case, I have y equals 1 as the solution. Does that work over here? Answer is yes. Because if y is 1, then dy by dx is 0, and I have 1 equals 1 over 1 squared, and certainly that checks out. We are now going to move from linear differential equations to autonomous differential equations. An autonomous differential equation can be nonlinear. Any equation of this form, dy by dx is a function of y and y only, is called autonomous. The word autonomous means self-governing, and so in a sense, y is determining itself without reference to x. Well, let's see examples of autonomous differential equations. So dy by dx equals 3y is autonomous. So is dy by dx equal to y into y minus 2 into y plus 7. That too is autonomous. So is this dy by dx equals e to the power y divided by y squared. But here is an example where you do not have an autonomous equation because there is x present over here. This is explicitly not autonomous. Now, these autonomous differential equations are important because dy by dx is f of y, and if f of y is 0, then obviously you have dy by dx equals 0, which means that y then becomes a constant. And that's an equilibrium situation, a non-changing situation. If we look at the equations up above, for this one over here, y equals 0 is an equilibrium solution. Over here, it is y equals 0, 2, and minus 7. But for this third equation, there is no equilibrium solution because e to the y over y squared is never 0. An equilibrium solution could be either stable or it could be unstable. And this is in fact something that we are going to concern ourselves with greatly. A stable solution means that suppose you start with y equal to some constant value, and if you were to add something to this, let's say delta y, so just remove the value of y from its constant value. The question is whether this will come back to this constant or not. Now, to make this point clearer, let's see an example. Here's an example of a stable equilibrium solution. This is something that we are all very familiar with. There's something hot, a cup of coffee, and there's something cold. This hot object will cool down, this cold object will warm up, and if the outside temperature is, let's say, 10 degrees centigrade, then both of these will ultimately come to the same temperature, to 10 degrees centigrade. Now, what possible equation could describe such a situation? Here's something that'll work. dt by dt, that is to say, the rate at which the temperature T is changing with time, is proportional to minus T minus 10. So you can see that if the temperature T is greater than 10 degrees centigrade, then dt by dt will be negative. So the temperature will decrease with time. On the other hand, this cold glass of Coke will warm up because T is less than 10, and so this minus sign, which is absolutely crucial, will cause the temperature to rise, dt by dt, to be greater than 0. Of course, there should be a constant in front of this equation here, a positive one, and these constants would be different for the coffee and for the Coke because they have different amounts of surface area and different ways of losing or gaining heat. But that doesn't matter for our purposes. Now, this is an autonomous differential equation, and it's one that's quite easy to solve. Let's solve it. We'll just use separation of variables. So we'll write this as dt divided by t minus 10 equals minus dt. And then we'll integrate both sides. So integrating this gives us log of t minus 10. And integrating this gives minus t plus some constant. So then we can write this as t minus 10 is equal to e to the minus t times e to the c, but e to the c is just some other constant, we'll call that a. To determine a, we'll use this initial condition that when t is equal to 0, the temperature is T naught, and so we get T naught minus 10 is equal to e to the minus 0, which is 1 times a. And so we found a. And therefore, t minus 10, we'll take the 10 to the other side. So t becomes 10 plus a, which is t naught minus 10 e to the power minus t. And so you can see that as time goes on, this e to the minus t will go to 0, and so t will tend to 10 degrees. So whether this t0 is larger than 10 or less than 10 doesn't matter. This t will become 10 as time goes to infinity. So t tends to 10 as t goes to infinity. Now, there's just one other point I want to make before we go on to look at this graphically. If I take the derivative of this, dt by dt, then I'll get d2t by dt squared, and that's equal to minus dt by dt. But dt by dt is minus of this, so this is t minus 10. So there's a plus sign in front of this. And that's telling us that the second derivative of t will depend on whether the temperature is bigger than the room temperature or less than the room temperature. I'm now going to make a plot of the temperature as it changes with time for the hot object and for the cold object. But first, note that this over here is t equals 10, and sometimes this is called the phase line. And we'll encounter many more phase lines in a few minutes. First, we'll start with the hot object as it cools down. So you can see that the temperature is decreasing and it gets closer and closer to the outside temperature, t equals 10, as time goes on. Now notice that everywhere the slope is negative. So let's say this point over here. The slope here is negative. And in other words, what we have is dt by dt is less than 0. You can actually see that from here as well. T is greater than 10, and so dt by dt is negative. You can also see that the slope is becoming less and less negative, which means that d2t by dt squared, the second derivative of the temperature, is positive. And of course, you can see that from here as well. Now for the colder object, let's start with the temperature being 2 degrees less than the outside. Then as time goes on, it gets warmer and warmer until it finally reaches this level over here, coincides with the phase line. Let's look at the derivative somewhere down over here. You see that over here, dt by dt, the slope is positive, and it's going from more positive to less positive. So d2t by dt squared, that is to say, the rate of change of the slope of this curve is negative. And of course, you can see that from here as well, because if t is less than 10, dt by dt will be positive, just as you can see graphically here. And d2t dt squared, that's going to be negative because t is less than 10. So the important lesson to take away from this is that this stable solution had dt by dt less than 0 up over here, and d2t dt squared positive over here, and it's exactly the opposite here. We'll now discuss unstable solutions. So here is the equation, but now with a positive sign instead of a negative sign. And this will mean that when t is greater than 10, the slope will be positive. And this is going to lead to an unstable solution. You can see now that if you start even a little above the equilibrium temperature, that temperature is going to go increasing and increasing until it finally reaches positive infinity. On the other hand, if we start even a little below the equilibrium temperature, is going to get colder and colder until it goes to minus infinity. Infinity in the other direction. So the point is that if you start even a little below the phase line, you go to minus infinity, less and less so, slower and slower though. If you're exactly at t equal to 10, then of course you remain flat, but even if you're a little bit above it, you again go to infinity, positive infinity. And so this is an unstable solution. Although we worked out the simplest of examples, yet we've learned something very valuable. For any stable solution of an autonomous differential equation, just above a phase line, the slope is negative and the second derivative is positive. Just below that phase line, the slope is positive and the rate of change of the slope is negative. Using this principle over here, we're going to find whether more complicated equations have stable or unstable equilibrium solutions. Let's now consider this autonomous differential equation. dy by dx is square root of y, y minus 1, y minus 2, and y is specified to be positive because we don't want the square root of a negative number over here. We're asked to find the equilibrium solutions and which solutions are stable. Well, the equilibrium solutions are trivial. Y equals 0, y equals 1, and y equals 2. If y is any one of these three values, dy by dx will be 0, and we'll have three phase lines. The question now is, which solutions are stable? And in order to know that, we will use what we've learned earlier up above over here. And now what we need is not just the first derivative, but also the second derivative. So let's take y double prime, d2y dx squared in other words. When we differentiate this, we'll get 1 over 2 square root of y. And then there'll be y minus 1, y minus 2, because we're not touching these. There'll also be the derivative of y, because this is not x over here. Remember, this is y as a function of x. So we have y prime here. Next, we're going to differentiate this, leaving the first and the second unchanged. So square root of y, y minus 2, y prime. And then finally, we're going to have square root of y, y minus 1, y prime. So you can see that the second derivative of y will be proportional to the first derivative of y. Let's look at the solutions graphically. So there are three phase lines, y equals 2, y equals 1, and y equals 0. These are obviously solutions of y prime equal to 0, and the question is whether these are stable solutions or not. So let's start with y equals 2 and look at a solution that starts just a little bit above. So it's 2 plus epsilon, and epsilon is a tiny positive distance up over here. So looking down over here, we can get the sign of y prime. Y prime is simply square root of 2. This will be close to 1. And this over here is then epsilon. So since epsilon is positive, we're just above the line, this is positive, which means that this solution is sloping upwards. So if we start from here, this is going up like that. What about y double prime? That we can get from here. When y is close to 2, then this will go away, and here there will be simply 1 times y prime, but y prime is proportional to epsilon, and that too is positive. So definitely this is an unstable solution. Now, what about down over here? When epsilon is negative, then y prime is negative, which means it's sloping downwards like this. And y double prime will be also negative. So that's telling us that this is unstable both on the top and on the bottom. Now let's come to y equals 1. So we look just a little bit on the top, y is 1 plus epsilon, and let's see what happens if we start somewhere over here. Y prime we can get from here, because here this will be close to 1, this will be close to minus 1, and this over here is epsilon. So y prime is like minus epsilon, and that's negative. Similarly, let's look at y double prime. So this doesn't matter and this doesn't matter, but this over here will be minus 1 into y prime. So that's minus of y prime, and that's like epsilon, and that is positive. So this is stable. And what that means is we've started just a little bit on top, and it's come down and it's bent until it coincides with y equal to 1. Again, if epsilon is negative, you're slightly down over here. In that case, y prime will be positive, and it's going to bend also upwards and coincide with y equal to 1. So this is a stable solution. Finally, what about this over here? So we'll take y close to epsilon, so just a little bit above this axis, and epsilon here will only be positive because there's the square root of y. Let's look at y prime. Look over here, that's square root of epsilon, and here we have essentially just 2. That number doesn't matter. The fact is that this is positive, and so this is sloping upwards like this. Moreover, looking over here, you can see that actually this y double prime becomes positive infinity as you go to y close to 0. And so the more accurate picture is that it's going up like this. And so if you started from here, it would go to this phase line and become the solution y equals 1 eventually. So this too is unstable. In this way, without actually solving equations, we have actually found the qualitative behavior of the solutions of this autonomous differential equations. And we've learned a lot. We've learned that solutions that start anywhere will go towards this stable solution. On the other hand, if you start either close to 2 or to 0, then you'll move away from 2 or 0 respectively. You saw in the various examples that solving even first-order differential equations can get a little tricky. For higher-order equations, differential equations, it can get much trickier. But the good news is that for any first-order differential equation, you can always get a solution numerically, and so do it by hand or with a computer or a calculator, and you can get the solution to whatever degree of precision you want. But of course, you have to have an initial condition for that. That was one of the major points of this lecture.